Okay, we have our discharge line coming out of our compressor. We have our discharge line continuing onto our condenser. Between it, we place an oil separator. We also have an oil return line that brings the oil back to the compressor. The refrigerant oil mixture pumped out of the compressor flows at high speed in the discharge line. The diameter of the oil separator is larger than the diameter of the discharge line. This larger diameter slows the oil flow down in the oil separator, which makes it easier to capture the oil aerosol droplets. The oil is captured as the flow passes through screens, baffles, filters, or certain piping arrangements within the oil separator. The oil that is captured falls to the bottom of the oil separator and is collected. The rising oil level will lift a float, almost like a, lack of better terms, toilet tank float, that opens a needle valve to allow the oil to return to the compressor crankcase or the suction line. In some installations, the oil will move into a separate oil reservoir before circulating in the crankcase or suction line. On hermetic systems, the oil return line is usually connected to the suction line near the compressor with a T-fitting. And that's because a hermetic compressor is sealed and we cannot pipe an oil separator directly into it unless there's a fitting for it. Coalescing oil separators can remove 95 to 99% of the oil components. They usually filter made of highly pure glass fibers. The material forces the molecules to combine and form larger droplets that are routed by gravity through a drain layer. A filter in the oil return line will keep the oil clean. A filter may not be needed if a coalescent oil separator is used, as it filters based on the glass fibers. Okay, this is an example of a coalescing oil separator. The oil comes in, flows through a filter, and then drops down to the bottom. Okay, as the float switch rises, it opens the line back to the suction line or the low side of the system. And what happens here is basically the high pressure on the high side of the system forces that oil back to the low side of the system. Liquid refrigerant can sometimes collect an oil separator during the off cycle or during long manual shutdown periods. The liquid refrigerant is heavier than oil, so the refrigerant will displace the oil in the bottom of the oil separator. An uninsulated oil separator may dispel enough heat to allow refrigerant vapor to condense into liquid. This is especially important in cold climates. If you have a condenser with an oil separator outside, and if the temperatures drop low enough, you can actually trap liquid refrigerant in that oil. Oil separators are often insulated to help prevent this from happening. A temperature probe is located under the insulation of the shell of an oil separator to allow for accurate readings. Another possibility is for liquid refrigerant in the condenser to migrate back to the oil separator. Liquid refrigerant may return to the compressor through the oil line by displacing the oil at the bottom of the oil separator. And again, we have to remember our compressor does not like liquid. This could result in too much liquid refrigerant and oil collecting in the compressor, which could lead to additional stress on the compressor, reduced lubrication, and damage to the compressor. The installation of a check valve in the vapor outlet side of the oil separator will stop liquid refrigerant from migrating backward through the system. A solenoid valve is sometimes used as well. It's usually installed on the oil return line. The solenoid allows the refrigerant oil to make its way back to the crankcase during the on cycle. The thermostat will close controlling the solenoid only when the oil separator is warm, usually around 100 to 130 degrees. The solenoid is de-energized during the off cycle to prevent possible liquid refrigerant migration that could cause a flooded start or slug the compressor. A liquid line solenoid is recommended on field installed systems with a large refrigerant charge over 3 pounds of refrigerant per motor horsepower. The purpose of this valve is to prevent movement of liquid refrigerant from the evaporator through the EEV or cap tube when the compressor is not operating. EEV stands for external equalizing valve. This is an example of a helical oil separator. Again, we have our inlet, okay, and the compressor, the inlet is from the compressor. Then we have an outlet. The inlet goes down through a helical sort of drop that forces the oil molecules to cool down enough and separate through the oil drain baffle. There's a secondary mesh screen also that's designed to help additional oil come out of the refrigerant. You have your standard ball float at the bottom, and when that float goes up to the top, it will actually allow the oil to come back through the oil return connection back to either the compressor crankcase or the suction line of the system. The helical oil separator is designed to allow refrigerant vapor and oil to enter at the inlet, flow downward along a spiral path of the helix. The centrifugal force of the vapor oil flow forces the oil to move outwards to the wall of the oil separator, where screen layer is located. The oil then flows downward through a baffle into a pool at the bottom. The screen layer serves two purposes. It helps separate the oil as it goes around the helix, and it allows draining because the oil molecules and droplets will drain down the stream. The separated oil flows down the interior wall of the shell. This arrangement causes a small pressure drop for high pressure refrigerant vapor. Helical oil fill separators allow 98% oil-free refrigerant to leave the device. An oil return valve returns the oil to the crankcase or oil reservoir. An oil reservoir is a storage vessel that holds an oil supply for the compressor or a group of compressors in a refrigeration system. Oil trapped by the oil separator is returned to the oil reservoir until it is needed. The oil reservoir may contain two sight glasses for observation of oil level and a flare fitting for adding oil to the system. This is an example of an oil reservoir. Okay. Okay. So here's an example of how we deal with, okay, this is a larger refrigeration system. You'll notice that coming out of the compressor, we go into the oil separator. Then we come out of the oil separator, this has a head pressure control in it, or the condenser. Okay, we go through a receiver. We come back here.